Hi everybody, in this video we're going to continue to talk about forces. Some of the main forces we're going to be talking about are weight and normal force, as well as tension, and also apparent force. So first of all, when we talk about forces, we have some static forces, which means that those forces are stationary or not moving. And then we have kinetic forces, which are forces that are moving. In this unit, we'll actually have both of those different kinds of forces. Here is a list of some of the forces that we will see. We have a lot of other forces that we can potentially look at, but these are some of them. Gravitational force, or as they're called, weight. Normal force, which is like a supporting force, and that force is always perpendicular to the surface. We have frictional forces. They can be air resistance or static friction or kinetic friction. And we'll actually have a separate video on frictional forces. And then we have tension, which is when something is hanging down or pulling it, usually from a cable or a string. In that case, the force is always acting parallel to the rope or cable or string. And then we also have spring forces that we'll talk about. We'll start off by talking about weight. When we talk about weight, we're really talking about force of gravity. So we know the force of gravity is just mass times gravity. That's the equation that we're going to use to talk about weight. And we're going to use, and usually we're going to use negative 9.8 meters per second squared. Of course, in the AP, they typically use negative 10, so it'll vary a bit. So when we talk about weight, of course, there are two concepts. There's one of weight and one of mass. And the main difference is, or one of the main differences, mass is a scalar unit. It's how much matter something has. It's in kilograms, that's how we measured it. Whereas weight is a vector quantity. It's a force of gravity acting on the mass, is measured in newtons. And so just keep in mind that mass is a scalar and weight is a vector. Weight is affected by how much gravity there is. So if you're on a different planet and there's different gravity, you'll have a different weight, whereas the mass does not change regardless of where it is. When we talk about weight, it is a vector quantity and it will always be straight down. It always goes in the negative y direction. And we've talked about this a little bit, but when we have our free body diagrams, we always draw that vector for weight is always straight down, and that's the force of gravity. And so we define weight as a force of gravity, and that's mass times acceleration due to gravity. And so we talk about a 10 kilogram object. We're just going to take the mass, 10 kilograms, multiply by acceleration due to gravity, which is 9.8 meters per second squared, and we're going to get our answer from there. So our answer just comes out to be negative 98 newtons. Now again, notice I have it in newtons, and just a reminder again that newtons is how we measure weight. In this class, a force or weight is measured in newtons, but a kilogram meter per second squared is equal to a newton. So if you just looked at this, it looks like it's kilogram meters per second squared. Short way to say that is newtons. All right, well, what if we take that same object, that 10 kilogram object, which was 98 newtons here on Earth. Actually, I should address just for a minute the symbol, the negative sign. It's negative 98 because the force of gravity is working downwards. And so that's why it's a negative 98. So just keep that in mind. So if we took that same object to the moon and gravitation is 1/6 of that what it is on Earth, then we would just take this number and multiply it by 1/6 or divide by 6. So I have the same equation, 10 kilograms, negative 9.8 meters per second squared, and now I'm going to multiply that by 1/6 because that's 1/6 of gravity, and that's going to give me a new number. So if you take this same object, that's 10 kilograms, has 98 newtons on Earth, it's going to be 16 newtons on the moon, which just means it's going to feel like it weighs less. Of course, it has the same mass, it's just going to feel like it weighs less. Okay, that's weight, and a slightly related concept is normal force. The normal force, some textbooks use N, like OpenStax. I actually need to go back and look at OpenStax, I'm not sure, but some textbooks use N. In AP, we're going to use F sub N. Normal force is a contact force. That means it comes into contact with it, which is what most of our forces are in this class, but not all of them. So it's the force exerted by a surface on an object, and it's directed perpendicular to the surface in contact. So the free body diagram, let's say this time that we have a 5 kilogram box, and our free body diagram is going to be based upon this dot. So we have the force of gravity working downward, and so then we have the normal force acting upward in an opposite and equal fashion. And so we still have the force of gravity, what I'm going to do is I'm going to calculate the force of gravity and then say, well, then the normal force must be opposite of that. And so here I have my mass times acceleration is negative 49 newtons. And so if this is negative 49 newtons, then the normal force must be opposite and equal. So it is 49 newtons in the positive direction for the normal force. So normal force and gravitational force are just essentially opposites of each other as long as there's nothing else involved. But sometimes there are other factors involved, and that's what we'll take a look at next. Okay, first of all, on your copy, I think this somehow came off with the formatting. So take a minute to maybe include that into your notes. A person pushed down on the top of the box with a force of 20 newtons. How would the free body diagram of the forces act change? I'm actually going to call that, instead of P, I'm going to call it F sub P. Again, different textbooks do it differently, but in the APA world, almost all of our forces we're going to use F and then a subscript for it. So that's the force of a push. So the force of the push being 20 newtons. Okay, how that would change the free body diagram? Well, you have this 20 Newton force acting downward. So the force of the push is acting downward. We also have the force of gravity, which didn't we find that to be 49 a minute ago? So I'm going to draw it a little bit longer because it is longer. And then our normal force ought to be equivalent to these two added together. And I've kind of run out of space. It might even be longer than this. So this is our normal force. When we talk about forces, as long as they are in equilibrium, remember if they're in equilibrium, then nothing is moving. If nothing is moving and they are in equilibrium, then the sum of the forces in the y direction, we're only dealing with y right now, should be added up to be 0. So in other words, the force from gravity plus the applied force, or we can call it the force of the push, plus the normal force should add up to 0. In other words, the force of gravity is mass times gravity. The force of the push we need to find. The force of the normal force we need to find. I'm going to come up here. So our mass is 5 kilograms, and our gravity is negative 9.8 meters per second squared. Then we also have the force of the push going downward, so I'm going to call that a negative 20 newtons because it is acting downwards. I need to add that to my normal force, and I'm running out of space, and set that equal to 0. Okay, so when I multiply this, I do get negative 49 newtons. This again is still my negative 20 because it's acting in the downward direction. If I subtract that normal force from each side, then I'm going to have a negative normal force over here. So I add these up, I get a negative 69 newtons, and that's going to be the negative of the normal force. So in other words, my normal force is 69 newtons. So the free body diagram changes because we have an additional force, this push force, being added on to the end there. Okay, let's talk about tension. The tension in a cable or a rope, and again, I have T here because this was a different book that I was using that used T. We will typically use F sub T for the force of tension. It's a force that is transmitted through the cable or the rope to the object and directed along the cable or rope away from the object. And so whatever you're attaching, you're going to be pulling with that tension, and it's going to affect the normal force. So we have the same box, the same 5 kilogram box, and if we had a cable attached and it was pulling upward, how would it change? So here I have this time I'm going to have the normal force, but I'm also going to have this force of tension, and that added up should equal the amount of the force of gravity. And my gravity should be a little bit longer because I know the tension is only 10 newtons and my force of gravity was about 50 newtons. Okay, so here's how I'm going to set this up. Again, because nothing is moving, I have the sum of the forces adds up to 0 because nothing is moving, nothing's accelerating. So what are the sum of the forces in the y direction? Well, we have gravity, we have tension, and we have normal force, and all of those have to add up to 0. So I've already calculated the force of gravity. That's mass times gravity. That is 49 newtons. Actually, I'm going to call it a negative 49 because it is acting in the downward direction. Now, the force of tension, this time the tension is acting upwards. So that's a 10 newtons, but it's acting upwards. And the normal force, well, here's the deal. Well, we'll talk about this a little bit more in the next little section here, but the normal force is really what we consider to be the reading on the scale. So if you're pulling up on something, it's going to appear lighter, isn't it? So I add these together and I get a negative 39 newtons. is the negative force of the normal force if I move that over. So in other words, the normal force is 39 newtons. So in this case up above, we were pushing down on it. That's going to make it appear heavier. On this one, we're pulling up on it. That's going to make it appear lighter. So the apparent weight changes depending on that. But tension is when you pull on something with a rope or a cable. And so that's what we're talking about in this next section, is the apparent weight. So the object's true weight is always mass times gravity. That's always what the true weight is. But then if we do something to it, like we tilt it or we pull it or things like that, then the weight, the reading on the scale is going to change. So if something was placed on a scale and then the system was allowed to accelerate upward or downward, the reading on the scale would not equal the true weight of the object. And so that's kind of what we were touching on here, is we're changing that apparent weight, what the reading on the scale is. So let's say we have a 5 kilogram block placed on a scale. What is the reading on the scale in the newtons? We've talked about that a lot. It is going to be 49 newtons. Let's say the block and the scale are accelerated upward with an acceleration equal to 2 meters per second squared. What is the new reading on the scale? Okay, what does this even mean? Let me show you what we're even talking about. Okay, what we're talking about is we have a box and it's on a scale. And I drew inside this scale a spring because that's probably how the scale works, is there are springs inside of it and we can measure how much force is on those springs. But then the scale and the box sitting there are sitting on something. And this might be an elevator. Maybe they're just in an elevator and the elevator is about to go upwards. Or maybe they're on some sort of a pulley and the pulley is about to pull it upward, okay? So that's what we have here. We have an acceleration 2 meters per second squared being applied to this. Well, think about it. If that happens, do you realize that this is going to kind of push that spring to be even tighter, and therefore won't the box have a greater apparent weight than when it started? Because you're pushing up on it, so it's going to push the scale, it's going to change the reading on the scale. So we still have that force is equal to mass times acceleration. In this case, our force that we're talking about, we want to know what is the normal force. Well, the normal force is going to be equal to the force of gravity, which is mass times gravity, plus the acceleration that's being added to it. So we have that original 49 newtons from before, and now we have an additional 10 newtons, because 5 times 2, that's going to be added to it. And so the normal force, being the reading on the scale, is equal to 59 newtons. I did a little bit of, I kind of skipped maybe some steps in here, because we know the normal force is going to be the opposite, so that's why we're getting a positive here. But the gravity is acting downward, and this acceleration force is also acting downward. The floor, whatever the floor is moving up, which is creating a force pushing down on the scale. And so our free body diagram here would be that we have the force that which is applied, and we have the force of gravity, and we want to know, okay, what's the reading on the scale? And the reading on the scale is the normal force. Let's turn the page. Okay, have you ever ridden on an elevator and when the elevator goes down, it kind of feels like your stomach is dropping? Like you're kind of almost in free fall? Maybe that would be more on a roller coaster, but sometimes on elevators we feel that a little bit too. So here we have the same diagram. We have the box, we have the scale, but this time it's like the floor is dropping out. Okay, if the floor is dropping out, then this scale is going to be a little bit relieved. It's not going to be all bunched up. Remember, when it went the other way, it got all bunched up. But this time we're going the opposite direction. We're going downwards, and so this time the force is going to be actually subtracted from the weight. And so I need to finish that in that top part of the equation. That we're going to subtract, let's call this force of gravity, subtracting the mass times acceleration. So we have this gravitational force, this weight, but then we're going to subtract the acceleration from the elevator. So we're actually going to get a 39 Newton reading on that scale. All right, that is going to wrap up our discussion of normal forces and weight and tension and apparent weight, and we'll hopefully get to do some lab activities in class.